And let me see, Todd, are you with us?
Yeah.
There we go. Todd, do you want to present now? We're about half an hour ahead of time, but
Yeah, it's fine with me.
okay. Well, why don't we do that then, and we'll come back to all the rest of the stuff in a Q&A session. Okay, well, go for it. And thank you for joining us, and thank you for the presentation.
All right. Well, this came about because I had a hunch, no, because I had a feeling that it needed to be expressed how the uncertainty principle relates to gravity. Because the uncertainty principle is probably the most, the foundations of quantum mechanics. So earlier we got to watch Sabina show us about the uncertainty principle, probably better than I could ever do. So here's a video of a dog surfing. And essentially, these equations up here are Heisenberg's equations, and we can localize the dog on the surfboard, and he's like toward the back of the surfboard. But can we localize the wave he's riding? I mean, the wave is underneath him, it's in front of him, it's behind him, so this is a behavior of waves, and it's natural the way this came out in the uncertainty principle. So waves have a wavelength in space and in time, and you can think of that wavelength as the twice the delta x, and the period of time is twice the delta t, and the values are complementary. So if you narrow delta x, the change in momentum, delta P, gets larger. And if you narrow delta T, the change in energy, or uncertainty in energy, however you want to look at it, gets wider. So, if you try to localize this wave, it's going to get large and the poor dog's going to get pounded. But whereas if you reduce it, and it's reduced the momentum, and it spreads out, then it becomes a nice, safe ride. So Heisenberg's principle don't change just because you're in a gravity well or out of a gravity well. To an observer far outside the gravity well, he could, do some measurements of what's going on down the gravity well toward a black hole or toward a star, and he would determine that Heisenberg's principle hasn't changed. So in that sense, angular momentum, which is the right-hand side of those equations, doesn't change inside or outside of a gravity well. And in order to try to express this clearly, and you'll see why I chose to do it this way, I introduce this, just a scalar kappa, which is a scaling factor for these variables. And it just shows the complementary nature, that if kappa is larger, then delta E over kappa is smaller, but kappa delta T is larger. And same here, if kappa is larger, then delta X over kappa gets smaller, but kappa delta P gets larger. And I believe these are what they call, like, the delta X and the delta E in this case are what they would refer to as a squeeze state. The kappa greater than 1 would be squeezing these variables. And then, but if you take the ratio of these in terms of creating units of force, you see that the kappas cancel out. So like angular momentum, the force is also doesn't change inside or outside of a gravity well. So these two constraints on our measurements, on our uncertainty, our ability to measure, and the behavior of matter are all that's required to derive gravity. And by that, I mean the relationships between space and time, energy, mass, acceleration, all that. So what do we know about gravity? Length is contracted in a gravity well. Clocks run slower inside a gravity well. And in terms of these relationships, the complementary values are scaled the other way by a proportional amount. So here, delta x over kappa gives us a length contracted x variable. X sub kappa gives us time dilation, t kappa, delta t kappa, but the momentum is increased and the energy is decreased. And again, kappa is just a scaling factor. So kappa is larger inside the gravity well. So scaling results in the reciprocal values, or the complementary values, I mean, of momentum and energy to scale the other way. So next slide. So if we take the ratios of these, then we get velocity is inversely proportional to kappa squared. Power is varies the same as velocity, inversely proportional to kappa squared. And the ratio of momentum to position, or momentum uncertainty to position uncertainty, is a mass current, has units of kilograms per second, and force, as we just said, is invariant with respect to changes in kappa. And so we're just taking the ratio of those values, and we see that, you know, how they scale relative to each other. So one unexpected consequence, and may not be unexpected for anyone who's seen the polarizable vacuum model, but since the force has to be invariant inside and outside of a gravity well, but space and time are not, then acceleration is not. And so acceleration scales as 1 over kappa cubed, which means that in order for F equals ma to be invariant, then mass must scale like m times kappa cubed, and then force doesn't change. So this is kind of unexpected to, you know, but it is if you know the other model, but it comes out here from the Heisenberg relationship regardless. And so now we're going to compare. The first column is just the observable values or expectation values. And then from the uncertainty constraints, go back one. From the uncertainty constraints, we have length contraction and time dilation and the scaling of velocity and momentum, energy, frequency, acceleration, and mass. And in the third column, we have the Schwarzschild solution of Einstein's equation in the radial direction. It is the ratio of these metric coefficients, which can be treated like a refractive index, as in Halputhoff's polarizable vacuum representation. So in that representation, it's easy to see the relationship. Kappa, or kappa squared, is equal to K, and K is the refractive index. And so looking at the relationships, the same relationships that we have for gravity are identical to the relationships that you get by matter obeying the constraints of the uncertainty principle. So right there in the foundation of quantum mechanics is gravity. It's matter obeying the constraints of the uncertainty principle. After I wrote this, I read a couple of papers, but none of them dealt with it this way. So I'm trying to present these relationships, all right? And so, but there's another relationship that is one that I've presented before at APEC and at Estes Park, and that is that you can treat the gravity as a damping factor acting on the oscillators inside matter. So zeta is a damping factor, damping function, and zeta squared represents that 2gm over RC squared in Schwarzschild solution. So introducing damping into the phase factor of the stochastic wave equation, it has the exact same effects. And so, what we've done here is move from a gravitational field described by a refractive index and to how that field affects matter itself from the perspective of a distant observer outside the gravity well. Gravity, or refractive index, acts on matter in a manner that is consistent with radiative damping or damping in general. In other words, the field acts as resistance to the harmonic oscillator circuits that make up matter. So if you treat matter as harmonic oscillators, then damping is like adding resistance to those oscillators. But if it was just adding resistance, then everything would basically collapse to nothing. But the commutation relations in quantum electrodynamics and quantum field theory are prevented from doing that by the 0-point field. So the 0-point field is like a source. And without that source, the electrons would spiral into the nucleus and vanish. So you can't support atoms, you can't support matter. So there's a balance, an equilibrium between the 0-point field and the decaying resistance I'm talking about in damping of matter. So the damping and the source are in equilibrium, and that equilibrium changes depending on the distribution of matter and energy, just like the right-hand side of Einstein's equation. So you have to have that equilibrium to balance things out. But it's this balance that sets the scales of these relationships, the kappa and the K, the refractive index, because our rulers and clocks are scaled by damping in the gravity well. And so when we use rulers and clocks that are variable to damping, we measure space-time curvature. We measure the Heisenberg uncertainties. So here's a table adding relative damping. You see the zeta, and it's just, you can see here that the refractive index and 1 over 1 minus zeta squared are the same thing. So it's just the, written inversely, but it's the same exact relationships for length, time, velocity, momentum, energy, acceleration, and mass. So the uncertainty principles basically set up these rules for statistical observations at the quantum limit, and general relativity describes an identical set of rules as a result of the gravitational field, and the radiative damping model describes the identical set of effects, but as the result of damping of the harmonic oscillators in matter. So why does this work? And the reason is the core of quantum mechanics is that we have quantized angular momentum. All of the fundamental particles in the standard model have quantized angular momentum. So it doesn't change inside or outside of a gravity well. Therefore, all the particles in the standard model must obey these same rules of relationships, because when the angular momentum is fixed number, h bar over 2, then those relationships have to hold. And so, fermions are spin 1/2, bosons are spin 1. All atoms the ML quantum numbers are all describing quantized states of angular momentum. So because angular momentum is quantized, everything scales according to those relationships in the previous table. And that's, the gist of the presentation. Now, what's next? What I have next, and before we go to Q&A, so I don't have to come back on, is some updates of some experiments and a really cool demonstration. Let me see here. I think I'm sharing the sound. This should work.
Coils, which is setting up a background magnetic field, which basically is pointing from right to left. I have it set so that when the
type in the chat if you can hear
pulses, it pulls the beam of electrons toward it. The gradient coil's in the back. You can now see almost 2 full rotations, and you can see the diameter is getting bigger. It's kind of going downhill because the coil is relatively small compared to the size of the Helmholtz coils. Give me another view on the top. In a nuclear magnetic resonance experiment, think of that spinning beam of electrons as your gyrating protons. And when the gradient is applied, they're going to lift in the direction toward that coil, just like this. And in doing so, they would lose weight. So it's the same experiment, just instead of spinning up individual protons, or in the case of alzaphan, individual electrons, this is spinning up a beam of electrons that, when placed in a gradient field, want to accelerate in that direction. Well, down the gradient. Hope that explains it. Now, how does this mimic a warp drive? Well, here I'm using the background coils. The background field is a pair of Helmholtz coils, which is setting up a background magnetic field, which basically is pointing from right to left on the screen. And then I am pulsing a coil that is behind the coil on the left to reduce its magnetic field, and thus creating a gradient. Right? So I'm applying the gradient field over a background uniform magnetic field. In space-time, we have a background relatively uniform Maxwell temporal field. It's a scalar magnetic flux density. If we apply a gradient field on top of it while initiating NMR throughout the entire vessel and everything we want to transport, then when the gradient field is pulsed, the ship and everything in it, everything that's resonating under NMR and APR will accelerate forward. And that's the warp drive.
All right, so what you saw there was cyclotron motion. It isn't quite a cyclotron because I'm not accelerating it on each loop, each pass through the center, but it's still cyclotron motion. And geodesic motion is what you get in general relativity when you take the derivatives of the metric potentials. And geodesic motion means that no work is being done. In other words, free falling is equivalent to an inertial reference frame. You don't feel forces as you're free falling in a uniform gravitational field. I mean, you do if you're in a black hole and falling toward a black hole and you get spaghettified, but in a field like the Earth, you don't notice that. In cyclotron motion, the magnetic field that I'm applying is not doing any work on the charged particles because the force is exerted orthogonal to the direction of motion. And as it changes scale, it's a torque, but angular momentum is conserved. And if we apply a gradient to the flux density from the Helmholtz coils, which is what I'm doing with the pulsing coil, the cyclotron motion of the particle will drift in the direction opposite the gradient or down the gradient, downhill. And since the force, because I'm still putting a magnetic field, and my goal, because I wound a big coil, bigger than the Helmholtz coil, to create the gradient so that I could get a nice uniform gradient. And the objective was to that the magnetic field lines stay parallel and orthogonal to the motion of the electron at all times, so that no work is being done and it's equivalent to geodesic motion. And I'm trying to conduct some experiments with this machine I got, which is a Lorentz force experiment demonstrator I got from Sci Supply. And it's pretty cool. I like it. It's fun. So at the quantum limit, at that spin 1/2 particles, fermions in general, we can write the angular momentum. And we see that, in the case of the cyclotron motion, the linear momentum is conserved. But when I turn up the magnetic field, the angular momentum decreases with the radius. And that's because the magnetic field possesses angular momentum. So when I'm adding magnetic field to it, the total angular momentum of the field plus the spinning electrons in that beam combine so that the total angular momentum is conserved. But the angular momentum of the electrons in the beam, not their intrinsic spin, but the spin of the beam, is losing angular momentum until, if the field strength were strong enough, that I can collapse that circle down to a single electron. Then we're dealing with this bottom equation here where the area is exactly like it should be in those relationships. So the scaling of those relationships is related to the scalar magnetic flux density. And that's what I call the Maxwell temporal field. And because gravity is not polarized like magnetic fields, but if you have a scalar magnetic flux density resulting from the divergence in the Lorentz gauge, and I use this as an example, it doesn't have to be Lorentz gauge, but it provides us with a nice conservation of magnetic flux, which magnetic flux is a quantized, count integer numbers of magnetic flux lines. It's quantized as Planck's constant over 2e. And so quantized magnetic flux, we have a conservation equation, and that is the Lorentz gauge equation. And so this equation on the right-hand side here is basically the divergence, and it's equal to 0, but that's a statistical average in quantum electrodynamics. It's not an absolute value. Over an average of many statistical observations, it'll average out to 0, but the instantaneous values are not 0. And so this divergence term is what I'm calling the Maxwell temporal field, because in using this, the magnetic flux, remember I said is quantized, but h bar over 2e squared has quantum units of ohms. So it acts as the resistance for the damping factor. So this scalar magnetic flux at the quantum limit acts as a damping factor, which causes the particles themselves to length contract and lose energy, lose power according to those relationships. And that's what gravity is. Excuse me. So, and the beauty of this is that changing the gauge potentials with a gradient while keeping the Lorentz gauge intact does not affect electromagnetic forces. E and B don't change. So the geodesic motion we were talking about is not the same as a regular, or I should say, not the same as the electromagnetic forces, because those are not affected by a gauge field. But if you're applying a gradient in the scalar gauge field, then it's different. It's geodesic motion. It's changing those potentials of the gravitational field. And I'll get to more of that in a minute. Okay, so the scalar magnetic flux results in time dilation. And the hypothesis is that the resonant or Compton frequency of fermions is a direct result of the instantaneous scalar magnetic flux density in the local environment and the gyromagnetic ratio of the particle. The random flux acts as resistance, damping the natural frequency of the quantum harmonic oscillators that make up matter, providing the damping factor and the transformations as shown in table 2 and table 3. So the time dilation, you have a damping factor, and that damping factor we equate to this. And this is basically a gravitational potential. And why is this a gravitational potential? Because the gyromagnetic ratio divided by the resonant frequency, okay, the gyromagnetic ratio divided by the resonant frequency has units of 1 over Tesla, 1 over flux density. And the part of the hypothesis is that I'm assuming that the background field that sets the scale of the resonant frequency, the Compton frequency of these fermions, that scale is being set by a background field of scalar magnetic flux. And so that gamma over omega naught represents the denominator, which is the background field. And then in the numerator, we have the applied field, and it's applied like in the case of the Earth, we have the Earth's field. So the equivalent of the Earth's Maxwell temporal field would be about 700 kilotesla. And whereas in a previous presentation, the one in September and the one here on APEC, I calculated that the gamma over omega naught was a field of about 4 billion Tesla. So what's causing gravity is a gradient in this numerator part. And the background you can think of like, it's the 0-point field plus Mach's principle. So it's the 0-point field plus all the fields from everything else that happened to be there at the time. Practical. Or at least we'd hope so. So then installing this damping factor into our previous equations, now we see that, Heisenberg tells us what we measure in space, tells us why we measure space-time the way we do. And then the radiative damping model tells us why our rulers and clocks change in this field. And now this scalar flux density allows us to control it. It allows us to create these fields, which are wide bandwidth, multi-spectrum, very wide bandwidth, like the 0-point field kind of field, but scalar magnetic flux, not polarized magnetic flux like my experiment demo here, which is really for illustration to explain it. But the scalar magnetic flux density is something that can be created, and it can be manipulated with a superposition of fields to give us control over the damping factor, and thereby create things like warp drive, gravity, anti-gravity, however we like, because we have control over that variable. So Maxwell field is basically the gauge potential, which can be written covariant or contravariant as a 4-vector. We call it the 4-vector potential. And then from that, we get the equations of motion. And from the equations of motion, the way they're written here, they've been symmetricized, so they look alike. And so what you see here is how the Maxwell temporal field, or the divergence of the 4 potential, appears in the equations. And here it is again. So this is known as the Lorentz gauge condition, and it's the divergence of the electromagnetic 4 potential. And this is that part. And we're calling that the Maxwell temporal field because it controls time dilation, as I explained. So this choice of gauge renders Maxwell's equations generally covariant, so they're not in conflict with general relativity. It also sets the scalar magnetic flux density to 0 arbitrarily, as in quantum electrodynamics, where it is 0 as a statistical average. And it gives us a symmetry and a conservation equation for magnetic flux. As I said, magnetic flux is conserved. And if you consider that A is the magnetic flux per meter, then this equation basically is a conservation of magnetic flux, just like we have an equation for the conservation of electric charge. And since Maxwell's equations are gauge invariant, changes in this field have no effect on Maxwell's equations, just like they shouldn't in a gravitational field. Maxwell's equations don't change inside or outside the gravity well. And so the gradients in this field result in a gravitation-like effects, including gravitational lensing, geodesic motion, and that are identical to those that have been previously attributed to the space-time metric of general relativity. So here's a way to reproduce those effects using electromagnetism. So how is this connected to the refractive index? And I was asked to explain this briefly. The results of passing through a refractive index. So think of this gauge, this part right here. This is the gauge transformation. Okay, so we have a voltage. Clicked it. We have a voltage, and from that voltage, we're subtracting the time rate of change in magnetic flux, and chi here is the magnetic flux. So that gives us a new voltage, which is, it's the same as, grounding at the positive side of the battery instead of the negative side of the battery. It just adds a scale to it. It doesn't change anything. And for the magnetic vector potential, we're adding the gradient in the magnetic flux. And this gives us, it just kind of like adding an offset in the electric current. I mean, this current was already moving in this frame. So these two things, what they end up doing is, if you're subtracting from the voltage, then you're increasing the scaling factor in the denominator, which gives us K E naught. And if you're increasing the magnetic gauge potential, then we're increasing mu naught because we're adding more to it than it had before. So we end up with K mu naught. And so you can think of this as it's the equivalent to like standing waves, where the scalar photons are being radiated by charged particles. And as they're radiated out through a refractive index, you get partial reflection. And in a partial reflection, the electric flux cancels and the magnetic flux adds. So it gives you a basis for having an increasing magnetic flux density, scalar magnetic flux density, toward the source of matter. Okay, so it makes sense in that regard. And one can think of this as a superposition of fields or superposition of potentials. Next, we're going to talk about a superposition of fields. And in this is similar to what I was demonstrating with the Helmholtz coils. And I have a field between them. And then I have here the beam of electrons with its magnetic field wrapped around it. And when I superimpose the two in that bulb, you know, what you're seeing in the bulb is really the mercury vapor as the electrons hit the mercury vapor, but it's what you're seeing is the magnetic flux on one side has constructive interference, and on the other side, it has destructive interference, and that causes the beam to go in a circle. And this is identical to what you get here in a warp drive. You get, consider if like, as this little warp ship, we're going around in a circle. And if it's going around in a circle, then you're getting destructive interference in the middle and constructive interference all the way around, just like we were just saying. But now in the case of a warp drive, we have the destructive interference in the front and constructive interference in the back. And it's this passing through that gives us, you know, the warp drive. So okay, so a lot of people, including myself, wonder why a warp drive can go faster than light. And Sabina has a video on warp drive, and basically the reason is because we assume it can. There's nothing in the literature up until very recently that ever talks about how to accelerate something from 0 to faster than light. In fact, Alcubierre's original equation is symmetric, so it has no front or back. It's not in any way a propulsion system. It's simply a piece of space moving relative to the rest of space-time, dragging its contents along with it. Now, he says, and everybody says, well, the interior is flat, so there's no gravity. Well, if the interior is flat and there's no gravity, then when the bubble takes off and accelerates, it's going to leave you behind. So it needs to drag you along. So it's frame dragging is what it really needs. And that's comes along with in the paper of with Bobrick and can't think of his name right now, the realistic warp drive paper, they talked about the shift vector, and that's what's needed. And here I'm using the same relationships I did before to get a gravitational potential. And then we take the 3 gradient of that potential and we get a shift vector. And it's this shift vector, which is the gradient in this magnetic flux ratio, that gives us the warp drive. Just like I explained in the video, it's the warp drive takes all the protons and all the electrons in your body, in your ship, everything. And it's like a particle accelerator where you're the one getting flung out of the accelerator. So all the protons spin and you pump them up using a magnetic field to run them up to a higher frequency, then put them in a gradient, a reducing gradient, and let them free fall back to their natural state. And it's doing this to everything synchronously that allows it to move with geodesic motion and without the passengers getting slammed against the back. So that's pretty much the presentation for tonight. And there is a slide with conclusions here, but I'm not going to read through them. I will putting up these most recent slides on my ResearchGate. So, so Tim, we can open it for discussion.
Okay, wonderful, wonderful. And how are you doing, Todd? Are you feeling okay? I know you were struggling a little bit.
Yeah, it hurts, but all right.
Oh, okay, okay. I think, you know, we got hay fever season coming up too. So let me do this actually, for just a moment. Let me mute you back out, and everyone, please put your hands together for Todd.